Hello everyone. So in the previous video we talked about how to use the periodic table to write something that's called the electron configuration. Essentially the address of where an electron is in an atom using the concept of orbitals, regions of space where an electron can reside. So that was the previous video, electron configurations. What we're going to talk about today is something that's analogous not to an address but to a map. So many times it can be useful to chemists to not just write the electron configuration but to draw an orbital diagram or a map of where the electrons are in an atom. Okay, so in this little video we're going to talk about what an orbital diagram is and the rules that dictate how orbital diagrams, maps that reflect electron configurations or an electron address, how those orbital diagrams are drawn. Okay, so in an orbital diagram, in an electron map, we still use the principal quantum number and the orbital letter in that map. But to show that region of space, to show that orbital, we draw a box. Or sometimes people use lines as well, as just to show the place where an electron resides. So for each orbital, either a box or a line is drawn, and then the notation for that orbital is written below it. So in the case for hydrogen, I have a 1s orbital. So boxes or empty lines for orbitals. And instead of superscripts, which is what is used in electron configurations for actual electrons, in orbital diagrams, in electron maps, we use arrows. Arrows represent electrons. Now, it doesn't matter to me if your arrow has a single head or a double head, as long as you use an arrow to represent an electron. Okay. Now, the direction that the arrow points is going to be important. We'll talk about shortly. But just know for now that electrons are represented by arrows. And when you put an electron in an orbital, you put it in the box or the space that you have labeled for that orbital. So for example, hydrogen's 1s1. It has one electron, so therefore there is one arrow, one electron in that box. I could write it like this, or I could write it like this. Either way is going to be fine. Okay? So that is how to draw orbital diagrams. And that would be for hydrogen. But what happens when you have multiple orbitals and electrons? You know, all the other atoms in the periodic table they use more than one electron, and they use multiple kinds of orbitals, as you learned in the previous section. Well, to make orbital diagrams for those atoms, you need to follow three main rules, and we're going to talk about them here. Those three rules are underlined in bold here. But all of these rules, I'm going to refer to this energy diagram here of orbitals to illustrate how to use those rules. Okay? So what I have here in this cartoon on the left-hand side, I have listed the orbitals for an atom, and orbitals that are at the bottom here have lower energy. Orbitals that are higher up have higher energy. And that energy, knowing that energy is important because that is where the first rule for doing orbital diagrams comes into play, which is called the Aufbau Principle. Aufbau is a German word that means building up. The Aufbau Principle just says that lower energy orbitals fill first. That means you put electrons in a 1s orbital before you put them in a 2s orbital, because the 1s that has a lower principal, that has a lower energy than the 2s orbital. So knowing that and looking at this energy diagram, hopefully it's apparent that you can see why when we fill orbitals that the 3d orbitals actually get filled before the 4p orbitals, but after the 4s orbitals. You can see how they're sort of in between here. That also reflects the trend that's on the periodic table for orbital filling. You've put electrons on the 4s orbitals before those 3ds from the transition metals. That's because, for reasons we will not talk about in this class, that's because 3d orbitals are slightly higher in energy than the 4s orbitals, but lower in energy than the 4p's. So the first rule is that when doing orbital diagrams, you fill lower energy orbitals with electrons first. Okay? And under that Aufbau principle is this point that each orbital has a maximum of 2 electrons. So if you look at the periodic table that you've been using when writing electron configurations, when you look at the 1s region, how many electrons total can go in an s orbital, regardless if it's 1s or 2s? The maximum is 2. So that's why for a 1s orbital, and for any s orbital, there is only one blank written, or one box, because each orbital can hold a maximum of 2 electrons. Let's look at the p's for a second. So look at your periodic table and look to see where the p region is on that periodic table. It could be either the 2p's or the 3p's or the 4p's. How many total electrons can you put in p orbitals? If you count over, you can have a total of 6 electrons. Well, if you can have a total of 6 electrons in a p orbital, but each orbital can only hold 2, then that must mean that I have a total of 3 p orbitals that are all of the same energy. That's because I need to be able to accommodate a total of 6 electrons. Okay. Same concept for the D's. Look at the D's on your periodic table. They're on the transition metals. D orbitals can hold a maximum of 10 electrons, but since each orbital can only hold 2, I'm going to need to have a total of 5 D orbitals available to accommodate those maximum number of electrons. Okay? So all of that is to say is that orbitals, regardless if it's an S, P, D, or F, each orbital can only hold a maximum of 2 electrons. But because the P and the D and the F region that we're not going to talk about, but because there is room for more than 2 electrons in P and D orbitals, I have to have a total of 3 p orbitals and 5 d orbitals. Okay? So you fill lower energy orbitals first. Each orbital, each house, can only hold 2 electrons. So how do I place electrons in orbitals that have the same energy? Meaning, if I was to place electrons in these 2p orbitals, how do I place them? They're all the same energy. Do I just fill them up all in order? That's where this Hund's rule or bus seat rule comes into play. If I have electrons that need to go in orbitals that have the same energy, then I half fill them first, and then only after I half fill them do I go ahead and completely fill them if needed be. So this is called the Hund's rule, but I also like to call it the bus seat rule as well, because when you get on the bus, let's say you're taking the bus somewhere, generally people like to have their own bus seat. They really don't want to sit next to someone they don't know. Same thing with electrons. An electron would rather occupy an orbital, a region of space, all by itself than share one. It will only share if it needs to share or if there's no other choice. That's why electrons, when given the chance, they occupy orbitals of the same energy first singly, and then only if they have to double up do they double up. That's called the bus seat rule, or Hund's rule. Then the final rule is the Polyexclusion Principle. That just states that if two arrows have to be in the same orbital, then their spins must be opposite. What that means for this course is that two electrons in the same orbital, in the same region of space, have to be written pointed in opposite directions. So, for example, I'm going to do one quick example now. We'll do a few more examples in the next video. If I was to ask for the orbital diagram of helium. Helium, if you look at your periodic table, helium, its electron configuration is 1s2. The orbital diagram for that, I'm just going to draw a line here from my 1s orbital. And how many electrons am I going to place in that orbital? I'm going to place 2. When I place those 2 electrons in that orbital, they have to have opposite spin. So that means pointed in opposite directions. So here's my first electron. Here's my second electron. So that would be the orbital diagram for helium. Okay. So these are the 3 rules that you need to keep in mind when drawing orbital diagrams, along with having your periodic table handy. In the next video, we're going to do several examples of how to draw orbital diagrams for particular atoms.